You type a prompt and watch a machine write complex software in seconds. Ask it about quantum mechanics, and it delivers a perfectly structured response. When an interface communicates with this level of fluency, we instinctively assume a persistent, human-like intellect sits on the other side of the screen. Treating a statistical algorithm like a human colleague is a mistake. It leaves users vulnerable to the machine's most baffling and alien flaws. Ask that same system a trivial question. Ask it to count letters in a word, or compare two decimals like 9.11 and 9.9. It fails. It will insist that 9.11 is larger than 9.9, delivering the wrong answer with the same unyielding authority it uses to explain physics. How does a machine capable of passing the bar exam fail to count a handful of dots? To use this technology effectively, we have to look past the performance of fluency and understand the specific mechanical constraints driving its logic. The first major quirk involves perception. Large language models do not see characters, letters, or words the way human eyes do. They process text as tokens, arbitrary numerical chunks. The word ubiquitous, for instance, is not 10 distinct letters to the model. It is processed as 3 opaque numerical blocks. Asking the model to index every third letter of a word is like asking a human to describe the atomic structure of a solid brick by looking at its surface. The internal components are invisible to the system. Spelling failures are a symptom of the data architecture, not a lack of general intelligence. This rigid architecture also limits the model's ability to perform sudden counting or mental arithmetic. Generating text sequentially, the network uses fixed computational power per token. Forcing an instant math answer crams the calculation into one step, causing errors. Prompting it to show its work distributes the load across multiple tokens, carrying intermediate results forward in working memory. This logic is grounded in hardware. Specialized chips perform millions of fixed algebraic operations for every individual token generated. The architecture requires sequence space to perform logical calculations. Without that room, the model is limited to what it resolves in a single pass. This brings us to the confident lies known as hallucinations. During pre-training, the model compresses the internet into its neural network. This acts as lossy compression, a blurry statistical map of knowledge rather than a database. When prompted for information past its knowledge cutoff, like the running mates for a recent election, the model relies on these blurry recollections. It generates parallel universe timelines based on familiar text patterns. Following this phase, the model is fine-tuned by humans to adopt a specific persona, the helpful, authoritative assistant. When asked for an obscure fact it barely remembers, the programmed urge to sound like a helpful human overrides the lack of hard data. It prioritizes the confident tone it was trained to simulate. Researchers measure these limits by interrogating the model on specific, obscure history, such as the number of championships won by a specific 1990s hockey goalie. Once the blind spots are identified, they can train the model to say, "I don't know," instead of guessing. A hallucination represents the model faithfully executing its persona. It maintains the confident style of an assistant, even when the underlying internet data is missing. Bypassing this unreliable internal memory requires leveraging the context window. The context window serves as the system's active working memory. Information placed here is perfectly accessible and directly influences the neural network's next prediction. If you need to summarize a chapter of a book, you will get a significantly higher quality result by pasting the text directly into the prompt, rather than relying on the model to recall it from memory. Effective use means providing the exact data up front, giving the system everything it needs to process in its working memory. Beyond providing text, we can command the model to use external tools to cover its cognitive blind spots. To count a massive set of items, command the model to write and execute Python code. This offloads the mental arithmetic of the language model to a flawless external calculator. When you command the model to search the web, it retrieves hard facts and imports them into its working memory, replacing vague internal guesses with verifiable data. Beneath the interface, there is no persistent consciousness. It is a statistical tumbler that resets to 0 with every new prompt you enter. Avoid the trap of autopilot. Utilizing this technology requires understanding its specific mechanical constraints and acting as a deliberate manager of its alien logic.